Hey, hello everyone. Welcome back to the Topos Institute Colloquium. Today we're very happy to have Cole Comfort talking to us about syntax and semantics for mechanical processes. So please, Cole, whenever you're ready.
Thanks for the introduction, David. Yeah, so please feel free to ask questions during the talk if you want. Something's confusing you. And today, this work is like I'm going to try to talk about just the kind of research I've been doing recently, not a specific paper, but just to try to motivate the research program that I'm trying to work on. And there's been various people involved. The first person I worked with was my supervisor during my PhD, Alex Kissinger, from this paper, Graphical Calculus for Lagrangian Relations. And then later on, I worked with Robert and Titouan. Robert's a postdoc at Oxford, and Titouan's a professor in Paris. And he wrote these two papers. And then the final person is Giovanni Di Felice at Continuum, and I'm working with him right now. I'm going to briefly touch on our work at the end of the talk if I have time. So to motivate my research, I take a very interdisciplinary approach. So I read a lot of physics, and then I'm really confused most of the time. So then I try to make it formal using tools from category theory. And then what I really like to do in particular is to give generators and relations presentations of these categories in physics.
Yep.
So I see it like it's kind of like a trinity of three things. On top, there's physics, which is often a bit informal. And then on the bottom left, there's the category theory. And I'm going to use mostly categories of relations, if you know what that means. And on the bottom right is like the string diagrams and the graphical, what is like the syntax. So on the top is physics, bottom left is mathematics, and the bottom right is computer science. And my research is kind of the intersection of these three things. And the way I see it is that physics oftentimes is kind of informal, but there's really good intuition that gives a lot of examples for me to work on. So the general overview of the talk, first I'm going to talk about graphical linear algebra, so how you can reformulate finite-dimensional linear algebra just using string diagrams. And then to kind of go more towards the physics side of things, I'm going to sketch really basic Hamiltonian mechanics and introduce some symplectic geometry. And then finally, I'm going to talk about the research I'm doing, which is combining these two things, giving string diagrams for physics, in a sense. So to start, I'm going to talk about not matrices, but affine matrices, because this is like how I see what I see as the basic building block of linear algebra. So if you take a field K, then the category of affine matrices has objects, natural numbers, and morphisms now, or pairs. So the first part of the pair is a matrix, and the second part of the pair is a vector, which is like the affine shift. And the identity is just the identity matrix and shifting by the zero vector. And you compose these affine matrices as follows. You take the two matrices and you compose them together, and then you act on the first matrix with the affine shift of the second, and then you add plus b. So this U should be an S. And it's a monoidal category, so there's a monoidal product. And basically, this is the direct sum of matrices, and then you stack the vectors on top of each other. And the monoidal unit is just the number 0. So yeah, I find generally I want to try to reformulate things in terms of pictures or geometrically somehow. So there's a way you can see affine matrices only using string diagrams. So there's this black copy generator, which goes from 1 wire to 2 wires, which is just this vector. And then there's like a 0 by 1 dimensional metric, 1 by 0 dimensional matrix, which is like you think of as discarding. And then this white one, which is like summation, and this white unit, which is like inserting the 0 vector. And for any element of your field, you're going to have this like arrow, which multiplies by that element of the field. And then finally, you're going to have this vector, which just shifts by 1. And you can find enough equations so that you can reason with affine matrices just using pictures. So first you make the white stuff a commutative monoid, the black stuff a co-commutative comonoid, and they interact as a bialgebra. And then under convolution, you have the axioms of a ring given by your field K. So all of these generators are natural with respect to multiplication. And then you have the convolution, which gives you like, if you take two vectors, you can sum them together. 0 just separates the wires in two. If you compose them, then they can smush together, and 1 is the identity. And finally, for the affine shift, it's natural with respect to copying and deleting. So using affine matrices, or using these pictures, you can basically do any matricial calculation that you want, but you can't talk about like images and kernels and subspaces and things. So there's a better category, in my opinion, which is of affine relations. And again, the objects are natural numbers. And now you think of the morphisms as affine subspaces, where I'm going to allow my affine subspace to be empty. So this consists of a linear subspace L, in addition to a vector, which you shift by. And the identity is just a diagonal subspace. And then the way that these things compose is relationally. So if you have an affine relation R from N to M and one S from M to L, then these are subspaces of K to the N plus K to the M and K to the M plus K to the L. So you just look at the elements in K to the M, and you form the relational composite as all of the vectors in K to the N plus K to the L, such that they have a common intersection in the middle, U. And again, the monodal product is given by the direct sum, and the unit is given by 0. But this is like now a lot more expressive than affine matrices. And that's really nice. Yeah, so you can take any affine matrix, take the graph of this, and you get an affine relation. And you can take the graph, and then take the transpose of the relation, and you get an affine relation going in the other direction. And these two ways of seeing affine matrices as affine relations generates all of the affine relations. So if you take the graph and then the transpose of the graph, you can ask, what are the equations that these satisfy? So first, the black monoid and the black comonoid. So one coming from the graph, one coming from the transpose of the graph. They interact to form a Frobenius algebra. And if you copy and then uncopy, that's the identity. If you unsum and then sum, that's the identity. And you have the unit and the counit cancel. And if you take multiplication by a number in your field, and then you compose this with the transpose, if that number was not 0, then that's the same as doing the inverse. And then you have these equations, basically, because this is a compact closed category, you can bend the wires around using either the white or the black nodes. And they're related by putting a -1. And finally, there's this equation that's like saying, if you take an affine shift by 1 and then you ask that 0, this is like the empty space. So it annihilates everything. And everything just becomes the same. So yeah, this was introduced in this paper by Filippo Bonchi and all of his co-authors in 2019. And I found it really nice because basically you can talk about all finite dimensional linear algebra just internal to this category without having to do any reasoning with matrices or it's just all geometrical, very nice. And I'm going to use this notation. So if you have a bunch of black things connected together, then I'm going to kind of fuse them together into a black node, independent of how many input and output wires there are. And similarly for the white one, except if it's connected by a shift. So like you have shift by 1 multiplied by a, so shift by a, I'm going to like absorb that into the splitter. And this will be really useful notation later on. Yes. So that's like my background to linear algebra using pictures, because I try to think of everything in terms of pictures. But the point of this talk is about physics. So how can we connect this kind of string diagrammatic graphical way of thinking about linear algebra to physics? So one thing we might want to do is to take affine matrices over the real numbers, say, and then refine things so that we only allow the affine transformations, which are like physically valid processes. So a physicist would say, we want this to represent the equations of motion of particles. And similarly for relations, I want to do the same thing, but I want to constrain the affine relation so that the morphisms correspond to different ways in which particles can flow non-deterministically between different places. And then the idea is, by doing this semantically about these categories of affine matrices and affine relations, I want to take the refinements and then create some graphical language and reflect the equations in the semantics in terms of string diagrams. So I can do the same thing of taking linear algebra and doing it in pictures, and try to do that with physics as well. Just take something in physics, turn it only into pictures and equations between string diagrams. So to do this, I'm going to introduce Hamiltonian mechanics very, very briefly. So in Hamiltonian mechanics, generally, the space of positions is represented by a manifold, usually over the real numbers. So position is not really enough to do a lot of physics. So in Hamiltonian mechanics, you work with phase space. So you take your manifold and then you take the cotangent bundle. So if any point in your position space manifold is a position, then a point in phase space in the cotangent bundle will be a pair of position and momentum. So if Q is in your manifold M, and then P is this new thing added by taking the cotangent bundle, which is your momentum. So in the case that the positions are in Euclidean space, then the cotangent bundle just doubles the dimension. So if you have n degrees of freedom of position, then the phase space where you account for when you also account for momentum, you'll have another n degrees of freedom for momentum. But that's kind of a degenerate example. In my talk, I'm only going to care about Euclidean space, but to get intuition for what's going on, I find it's helpful to work with position manifolds, which are not Euclidean. And the simplest Euclidean manifold is the circle. So a physicist would call this angular momentum. If your position is constrained to the circle and you take the cotangent bundle, then this produces the cylinder. So it's a circle, and you take the product with the real line. So consider like a rigid pendulum. So this dot in the middle, it's like pinned to the wall, and then there's this rigid bar with some dot which is like can swing around the circle. And in this case, the position is an angle on the circle, and the momentum is like the length of this vector. And if you look at all of the positions and momentums that this pendulum can take, all of the different configurations of position and momentum, then you'll find yourself on the cylinder. So the angle is the position. It tells you kind of where you are on the circle, and then the position, it's really, really fast in a counterclockwise direction, it will be like really high, and if it's really slow, it will be near the center, and if it's really fast in a counterclockwise direction, it will go down here. But the point is, any configuration of this pendulum you can kind of think of in terms of its position and momentum on the cylinder. And in physics, position and momentum can take various different forms. So I took this table from John Baez's and Brendan Fong's paper. So the example I was trying to sketch initially, the position is usually denoted by Q, and the momentum is by P. And the derivative of position with respect to time is called velocity, and the derivative of momentum with respect to time is called force. And in this rotational example, Q is called the angle, the position is the angle. The derivative of this is angular velocity. P is angular momentum, and the derivative of angular momentum with respect to time is torque. You can do the same thing in electronics. So you have current, charge, flux linkage, which is kind of a non-standard term, and voltage. In hydraulics, you have volume flow, and then pressure, where pressure momentum is just kind of like not usually used, because Hamiltonian mechanics came after Lagrangian mechanics. So usually in the past, people were more used to thinking about velocity instead of momentum. And in thermal mechanics, you have entropy and temperature. And if you take the derivative of temperature with respect to time, you get like your notion of momentum here. So that was my my kind of very basic introduction to the physical side of things, but there's a very, very nice mathematical setting in which you can work that makes the physics a lot easier to manage. So if you take a manifold M and you take the cotangent bundle, which is your space of position and momentums, then this naturally is a symplectic manifold. And if your positions are your Euclidean space, then you get what's called a symplectic vector space. And I'm going to work with vector spaces because manifolds just become too complicated to try to formulate in terms of string diagrams. But you can see a symplectic vector space as a vector space equipped with a bilinear form, which has a bunch of nice properties. And a symplectomorphism is a map between two symplectic vector spaces, which preserves this bilinear form. And in particular, in finite dimensions, if you take a symplectic vector space, you can always show that it's symplectomorphic to a symplectic vector space of even dimension. So you can kind of take your vector space and then say half of it is going to have your positions and the other half is going to have your momentums. And the symplectic form is just the wedge product. So if you work with 1 degree of freedom of position, then this will just be r squared. And this is just the area of a parallelogram in the plane, what it's capturing. So to give the relation to Hamiltonian mechanics, I'll very, very, very briefly sketch how you can get the equations of motion from a Hamiltonian, and then I'll give an example, which is more informative, but just to show this is like real mathematics. So what physicists will do in Hamiltonian mechanics is they'll take their phase space of position and momentum, the cotangent bundle of their position space, T star of M, and they'll define a smooth function into the real numbers. And what this does is it takes your particles, essentially, and then gives you a number, and you think of this number as the energy. And if you take the derivative of this, this gives you a gradient. And then the symplectic form gives you this vector bundle isomorphism. And if you take if you take the inverse image of the symplectomorphism, you get a vector field, the Hamiltonian vector field. And then if you take the exponential of the Hamiltonian vector field, you get your time evolution. So now this is an endomorphism on your phase space of positions and momentums, and it just tells you how particles will flow after one step of time. So the way I think of this is that the equations of motion in general are like kind of hard to work with, but if you just change the way your way of thinking and just work with symplectomorphisms, then you get a really nice algebraic setting in which you can do physics without having to actually do physics. So here's an example to kind of illustrate this principle, because the last slide was very terse. So this is the Hamiltonian for an oscillating spring just going up and down with no friction over and over again. So it takes the position Q and the momentum P, and then the energy is defined as this function. And if you plot the energy as like a 3D graph where position is on the left and momentum is on the right and energy is going up and down, then you get the surface. So when you take the gradient of this, what you get is a bunch of like little arrows which point in the direction where energy is like growing the quickest. And then if you do this, if you apply the symplectic form, and basically what it does is it rotates all of these little arrows 90 degrees. So now they're all going in a circle. And the idea is if you start on some point on the surface and you follow the arrows, the energy will always remain the same. So energy has to be conserved. And it kind of tells you how things can flow without ever changing the energy. Just starting from this function, which gives you energy, you can get the flow. And if I just forget the energy now and just project onto the plane, you see that the flow generated by this Hamiltonian for the oscillating spring is just a rotation. Because you're just following these arrows around, and rotating uniformly by this angle theta. Yes, so the exponentiation of this is just the rotation matrix. And yeah, I said I'm not going to work with smooth manifolds, just vector spaces, because it's too complicated. But even vector spaces and Hamiltonian mechanics with vector spaces is itself too complicated. So I'm going to like look at an even more restricted fragment of physics, and that's where the Hamiltonians are given by quadratic polynomials. That is to say, you take your vector, which contains your positions and momentums, and then you conjugate it with a symmetric matrix A, which is like your quadratic term, and then you take the inner product with the vector B, which is like your linear term, and then you just have a constant C, which is your constant term. And if you do all of the math, then when you exponentiate the Hamiltonian and so on, you get a symplectomorphism of this form. So the first component is the linear transformation, and the second one is the affine shift. And this big omega is basically just witnessing the symplectic form. But yeah, so for example, if you take a quadratic Hamiltonian which does this kind of polynomial, like in our example before, where A and B were 0, then if you do this whole business with the exponentiation and so on, like above, then you'll get a rotation about the point AB in the plane. Okay. So just like I said before, how you can take a affine matrix and get affine relations, I'm going to try to do the same thing with symplectomorphisms to get a notion of relations which respect the symplectic form and these physical laws. So given the linear subspace of a symplectic vector space, the symplectic complement is a linear subspace where all of the vectors in the subspace are orthogonal to the original subspace, except instead of being orthogonal with respect to the inner product, it's going to be orthogonal with respect to the symplectic product. And an affine Lagrangian subspace of a symplectic vector space is an affine subspace where the linear part of the subspace is orthogonal to itself under the symplectic form. So this is something you don't get if you just work with the usual inner product. And the idea is these affine Lagrangian subspaces generalize affine symplectomorphisms via the graph. And affine symplectomorphisms generalize the equations of motion of quadratic Hamiltonians. So basically, you can work with these affine Lagrangian subspaces without ever having to work with Hamiltonians or do physics, really. You can just have this nice synthetic setting, nice algebra, and things are much, much more clean for me as a mathematician compared to having to do actual physics. So if you take your affine symplectomorphism and you take its graph, you get an affine Lagrangian relation, which is this kind of what I was alluding to earlier as this like affine relation, but it's more refined in the sense that it has to respect the physical structure given by Hamiltonian mechanics. So just like for affine relations, there's a category of affine Lagrangian relations. And again, the objects are natural numbers. And now the morphisms are these affine Lagrangian subspaces. And note that for an object being n, and the level of morphisms, it corresponds to a subspace of k to the 2n. So the 2 comes from the fact that now every object kind of inside of it, there's not just a position, but also a momentum. And all of the other rules of like the identity composition, the monadal structure is the same as for affine relations. So really, this is a refinement of affine relations in a way that respects some sort of meaningful physical structure. Yeah. So again, this generalizes the equations of motion, but moreover, because now things are relations, it's kind of you can represent not just the equations of motion of particles, but rather the different ways in which particles can flow in a non-deterministic setting, manner. So it's the morphisms now are kind of constraints saying how things can flow rather than only being the deterministic evolution of particles according to the equations of motion given by Hamiltonian mechanics. So during my PhD with my supervisor, Alex, we gave generators for this category of affine Lagrangian relations over any field. So the diagrams on the right are these string diagrams for affine relations, which I was drawing earlier, and the generators on the left. So you have, again, two spiders, but now there's more of these like phase labels. So for the black spider, you have a label A and a label B. And if you forget about the label B for a moment, basically what this is saying is this makes sure that all of the positions are the same, and it sums the momentums. And dually, for this white spider, it sums the positions and asks that the momentums are the same. And then this this B thing, what it's doing is it's taking the position, copying it, multiplying it by B, and then adding that to the momentum, and dually for the other color. So it's this nice symmetric thing, whereas before for affine relations, the string diagrams like only had a label on the white spider. Now everything is like completely symmetric, which is very nice. And to get some idea for what these are doing, if you just look at a spider with one input and one output, the B is acting as a shearing operation, and the A is acting as a shift. So this one, it shears the position into the momentum and then adds a affine shift on the momentum, and dually this shears the momentum into the position by B and then adds something to the position.
Sorry, Cole, I'm not seeing the
Yeah.
difference between the black AB and the white AB at all. What is it again?
The black.
The
It's
black,
just
the
so
black and the white diagrams, how are they different?
yeah. So the idea is that so every wire here, it kind of has two wires inside of it, and the one on the top is the position, and the one on the bottom is momentum. So so if you take this wire here, you split it in two. Now this is copying the position, whereas this one is summing the position. So it's, I mean, it's completely dual, but it's just
you can't
one
see
of them
the
is
diagram
acting.
itself, right? The diagram itself doesn't portray the fact that every wire on the left has two pieces in it. This is something you have to keep track of.
Yeah, it's like the monoidal strength of the functor, because yeah, you could also label the wires, but basically on the boundaries of these diagrams, all of these wires have two dimensions. Like this is k squared, k squared, k squared, k squared. Same here, k squared, k squared, k squared. And then on the inside, these are just k.
Got
So
it.
you kind of have to, you split to interpret it as an affine relation. I'm just like splitting the two wires apart and then doing things to them. But and the difference between the black and the white one is I'm just doing one thing to position on the one and another thing to momentum on the other.
I see. So those tensor boxes are isos, is that right? Or
Yes, yes.
and these are inverse isos on the left and right, and they split into a particular order, position first,
Yeah.
then momentum. Okay, got it.
Yeah, the order yeah, the order really matters. Yeah, so if you think of this as a monoidal functor, then these are the laxators, the monoidal laxators, and it's strong monoidal, so that yeah, they're invertible.
Got it. Thank you.
Yeah. Okay, and then in a later paper with my co-authors Robert and Titouan, in terms of these string diagrams, we gave enough equations so that you can reason about this category of affine Lagrangian relations only using pictures. I'm giving this axiom table just to give a feel for what this kind of research is like. Not that you can just look at this and understand it immediately, but you have these very nice rules so that you can think of things as labeled graphs. And when the two spiders of the same color are connected together by a wire, you can just fuse them together and then sum their labels. And then this box without a label. This is the symplectic Fourier transform. So this is allows you to relate position and momentum together. And you can derive it basically in terms of 3 shears, because the Fourier transform in a sense is a rotation. So you can derive it from these other generators. But so basically for this kind of fragment of mechanics, you get this nice graphical language. And basically it's a version of the ZX calculus, which was invented for quantum mechanics. But there's not necessarily any reason why it's inherently quantum at all. It's just a general physical thing that arises. So to give an example, if you think of a position in the phase space as a particle, so a pair of position and momentums, you can represent this as an endomorphism on a wire. So if Q is your position and P is your momentum, you can kind of think of this as a particle. So for electrical circuits, Q is the charge, the position is the charge, the change of charge over time is the current, and the change of momentum over time is the voltage. And we're going to think of these black spiders as basically just like wires that have been soldered together. And there's this law in electrical circuits where voltages across wires are equal, but charge is conserved. So by equal, they have to be exactly the same, but by charge being conserved, only the sum has to be the same. So if you take your particle with a position and momentum, and it runs into a wire which splits in two, the position has to be copied, but there's different ways in which the particle can flow through the wire. The momentum can like all go into the top wire, or some of it can all go into the bottom wire, or it can go in various combinations as long as the sum is the same. So this is what I was talking about when I was saying that these are kind of non-deterministic constraints on how mechanical systems can evolve, because there's various different ways that things can flow, but in this category, using the syntax even, you can show that these are all the same because of these underlying physical laws, which are represented using symplectic geometry. So to give more examples, an engineer would say that a resistor doesn't dissipate energy, so it doesn't create heat, which obviously isn't true, but in practice, unless you're working on a very small scale or you're working with a lot of resistors, you can kind of ignore the heat which is dissipated. And in that case, you model a resistor as having this Hamiltonian. So it takes the position Q and momentum R and just forgets about the momentum, and then squares the position, and then multiplies by the resistance over 2. So if you do all this business with exponentiating Hamiltonians and so on, then you get that this is a symplectomorphism, which basically just shears the momentum. So if you take 2 resistors and you compose them in parallel, then by using this spider fusion law, which I had in the previous slide, then the resistances just sum. However, now we have these wires which can split in 2, which allow us to do like non-deterministic things. So if you take a wire, split it in 2, and you put one resistor on the top wire and another resistor on the bottom wire, and then you fuse the wires back together, then you can use the equations which I gave, and then get the rule for composing them in parallel, just using the string diagram. So you take your resistor, and you take the Fourier transform, which changes the color and inverts the label, and then you fuse them all together, and then you invert the label again to change the color. And this is the formula which engineers use to like compute how resistors are composed in parallel. So these generators which we've chosen are like very canonical in a sense, because the basic things that you will do in these kinds of mechanical systems have a very simple representation. Like the wires are just these spiders, and the resistors are also just spiders with the resistance on the second phase. But yeah, originally my motivation was not coming from classical mechanics, but rather from quantum mechanics. So before I was working over the real numbers, but remember that I said that all of this stuff with Lagrangian relations and this equational theory, which I described, works over any field. So if you have an odd prime number p, and you take the finite field with p elements, then these affine Lagrangian relations over fp can be embedded into finite-dimensional Hilbert spaces modulo scalars. So you just quotient by any non-zero scalar. And whereas the monoidal product in affine Lagrangian relations is the direct sum, in Hilbert space it's the tensor product. So this is like a very particular subcategory of Hilbert spaces, a very small one. So this is an interpretation. What it does is it takes your objects, which in affine Lagrangian relations are just natural numbers, and it generates the group algebra. So it takes the complex, it generates a complex vector space where the basis elements are elements of fp to the n. And in quantum information, it sends states to what people call stabilizer states. And the morphisms are sent to what are called stabilizer circuits. To properly define this, I need to do some representation theory, which would take too much time. And the isomorphisms, so the affine symplectomorphisms, are sent to what are called the Clifford operators. So this whole story that I told about classical mechanics works for quantum mechanics when you take the field to be fp rather than the real numbers. So you have your quadratic forms, which are now over fp, right? So this is like the finite-dimensional quantum analog of a Hamiltonian. It's a quadratic function from fp to the 2n into fp. And from this, you can get an affine symplectomorphism, basically by doing the same thing I had before. Or you can get a Clifford operator. And all of these three ways of thinking of things are equivalent. And yeah, this was my original motivation for studying this stuff, because stabilizer circuits are like a very, very important class of circuits in quantum information. In particular, like basically all of quantum error correction involves using stabilizer circuits to correct against errors. And basically the point is that they're using symplectic geometry. They're taking positions and they're embedding them in a space of position and momentum, and they're kind of using this redundancy of position and momentum to encode things in a way that protects against errors which can occur. But surprisingly for me, I originally only cared about this, and I found classical mechanics and Hamiltonian mechanics just emerge naturally, and basically you have exactly the same picture in classical mechanics and in quantum mechanics. And so yeah, the previous few slides was about the one paper I wrote with Robert and Titouan, but we also want to go a different direction, because in continuous variable quantum mechanics, so now we're not just working with finite-dimensional Hilbert spaces, but infinite-dimensional Hilbert spaces of square integrable functions, then it doesn't make sense to talk about particles as points anymore, basically because of the uncertainty principle. And similarly, in classical statistical mechanics, you don't talk about particles as points. Rather, you think of particles as being probability distributions. And the ground state in quantum mechanics is not represented by a point now, but a probability distribution in phase-space. In particular, it's the Gaussian probability distribution in phase-space. So if you take, here is your positions and here's your momentum, the ground state, the vacuum state with no particles, is a probability distribution around centered at the origin. So kind of the density of the probability distribution tells you how likely it is to find a particle at some position in momentum. So this is a bit more complicated, and in quantum information, the tools are kind of not as developed as for finite-dimensional quantum mechanics, because there's a lot of analysis involved. But by shifting to this kind of phase space relational approach, we find a very, very nice semantics for this Gaussian mechanics. So if instead of working over the field of real numbers, if you take affine Lagrangian relations over the complex numbers, and you impose that every subspace satisfies this condition. So if you take a vector in your subspace and you apply the symplectic form with its conjugate and you multiply by I, and you ask if that's greater than 0, then this gives a semantics for Gaussian quantum mechanics and these probability distributions. One way you can think of this is you take these pictures I was drawing and you can restrict the labels on the spiders. So the first label was this affine shift. You ask that these are real numbers, and then you ask that this shearing operation is a complex number, but whose imaginary part is greater or equal to 0. Then you can represent Gaussian quantum mechanics. In particular, if you take A to be 0, B to be 0, and C to be 1, then you recover the ground state. And we showed that if you take this equational theory for affine Lagrangian relations over the real numbers, and you add a single new generator corresponding to this ground state, which represents this Gaussian distribution in phase space, then you only have to add 3 equations to become equivalent to this category I'm describing above, namely that it's invariant under rotations and that you can discard it. So the first equation is like saying you take a rotation and you decompose it into 3 shears. The idea is if you act on the ground state by this rotation, you're rotating this thing around and it does nothing because it's completely symmetric. And the second equation is kind of like a higher dimensional analog of this, where you have a bunch of different particles on different modes, and you're kind of rotating them between themselves rather than inside of the position of momentum. And you ask that it's also preserved. And just with these 3 equations, you can recover Gaussian quantum mechanics. So that was I found this pretty remarkable and very nice when we found this, because Gaussian quantum mechanics is very complicated, but through phase space, things become a lot simpler than you might expect. And I also want to talk about this work I'm doing with my co-author Giovanni, because so far everything I've said so far, there's no notion of time. So we thought, is there a way we can add time dependence to these physical processes? Because we really started with a very, very restricted class of physical processes. No time, that the Hamiltonian is quadratic. This is very restrictive. So I'm trying to kind of build up, get more and more expressive classes of circuits and physical systems. So the idea is we want to add a single generator to the syntax and think of it as just a discrete delay in time. So just like waiting for a second or something. And what you can do is, instead of working over your field K, you work over the rational functions. So these are fractions of polynomials. So work with affine relations over fractions of polynomials. You can interpret this generator as just something which multiplies by the polynomial indeterminate. So this is the graph of multiplication. It takes your position and momentum and then just multiplies them by delta. What we've shown in this paper we're writing is that if you do this, then you no longer get affine Lagrangian relations, because multiplying by delta kind of messes up the symplectic form. But what you do get is all of the affine Lagrangian relations, which are kind of Lagrangian, but with respect to this shifted symplectic form, where you take your original symplectic form and then you, on one side, invert the argument. So it seems like a very minor change, but it's surprisingly changes things quite a lot, and the structure becomes quite complicated. So just as like a teaser, here's the equational theory now that we have when you've added time. So all of your spiders are now like labeled by rational functions, and the second component has to be a rational function, which when you take the argument and invert it, it remains the same. You now have like all of this cool algebra that we had before, and except now you have this time label. And the last thing I wanted to say is, yeah, the idea of this talk was not to give like super technical definitions or give proofs, but just to try to motivate why this is something worthwhile working on. And my motivation really is like cool geometric pictures. So this is one of the pictures that I took from the paper we're writing. So you have this like this string diagram from the previous slide, and it kind of represents a graph, but now the graph is this like weird like infinite thing, but somehow you can tame things and reason about them using these simple string diagrams, when semantically you're kind of, it's unfolding into this cool spiraling pattern. So the point is like, just by adding more and more things motivated by physics, you get this really nice category and like cool pictures the whole way through, which I find very nice and symmetric and beautiful. And that's the end of my talk.
Great, thank you, Cole. So if anyone wants to ask a question, you can press the react button and raise your hand. Cole, how do you think of the particles as endo maps? Like a particle you said was like you know what I mean? You had this string and you had these two, a white and a black, and you said you can think of that as a particle. Like philosophically, what does it mean to think of a particle as an endomap of that string?
Yeah, I mean, it's kind of like philosophically a bit wrong, but it's more like if you think of a particle as an element of your phase space, so here it's a position and momentum, then this is like the action of that on that space. So it's like the thing which is like kind of changing the space by that particle, because the particle is really a point, which is like a state, but I'm just taking like the action by addition on the space. So because like really the particles are like probability distributions on the space, not endomorphisms. But in this kind of simplified setting, you can, where they're points, you can kind of think of them as acting on the space. But yeah, then you can think of them as flow. Yeah.
Is there something about when two of them come into contact, or when you transform the space somehow, that they like commute past that transformation? Or is there a way to say more about how those endos work with other endos on the same space in terms of physics?
Like yeah, it's really not like a single particle, but the way to think of it is like a bunch of particles that are like flowing. This is just kind of intuition. So like, yeah, here you can kind of think of two different particles flowing with a certain position and momentum. They're fusing together into like another particle, but it's not really like you had two particles in one. You just have two things that are flowing, and they kind of flow together into one thing. Similarly here, like two things which are flowing in parallel, then it behaves the same as just a single flow.
Gotcha. Okay, let's see if there's any questions. No questions yet other than mine.
Sure, I can ask something. Can you guys hear me all right?
Yep.
Yeah. Thanks for the talk, Cole. Do you mind if it's possible in a small amount of time drawing out a little bit how you got these finite fields popping up and you have sort of finite fields, which I could think of something about error correcting codes that sounds plausible, but there's also Hamiltonian mechanics in the finite field, or everything Hamiltonian is over C. I'm trying to indicate the amount of lack of clarity I'm at so far. I don't know if you could stabilize that at all.
Yeah, so like in quantum mechanics, like most quantum information is done in like finite dimensions, and you'll work with like q bits or q dits. So you think of like a state as like a d-dimensional vector, say, or here a p-dimensional vector, a single state. And in a sense, this is kind of like discrete. So you have like this representation of the Pauli group in finite dimensions, where you have your Pauli operators, which are like translating the position and momentum, and you can do like much more complicated things in quantum mechanics, but stabilizer quantum mechanics is like really nice because it has this representation which makes simulation, for example, efficiently possible. Because here the monoidal product is the direct sum, and here it's the tensor product. So this is like
Right.
kind of capturing the fragment of finite dimensional quantum mechanics, which kind of behaves like it's classical. So people will say this is like semi-classical mechanics. Whereas on the other hand, this is like quantum mechanics in infinite dimensions. And you don't have this discreteness anymore, and your particles become probability distributions. But they're both quantum mechanics, but very different flavors in a sense. And
Right. I guess I was wondering particularly about not just the finite dimensionality, but about the finite field in particular, right? Because you were upgrading Lagrangians. It seems how like algebraically or number theoretically interesting or something is the fact that you're actually in a finite field and have Lagrangians on there. Is that really substantial, or is it more like, oh well, finite fields could be somewhere where you can do some combinatorics of bit strings? Like, would there be any kind of connection to the more substantial mathematical areas where you run into finite fields, or should I not be thinking of that?
Basically, the reason why finite fields arise is because you're working in finite dimensions, and computer scientists work with like bits and dits and things. So the finite field here is really like a bit, but now it's doubled. So you have like the position and momentum, but also everything is like affine. So the mathematics is not so complicated. But also the point is, I said P has to be odd.
Yeah.
So this doesn't actually work for bits.
So it's not actually bits, but other than that, it's sort of as if how I can think of F2 as being related to bits. Yeah, that makes sense.
Yeah, and for F2, the representation theory fails, and then things become a lot more interesting mathematically, actually, and then you have to, it becomes quite complicated for F2. Yeah.
Right. Fine. Yeah. Thank you. Thanks. That clears that up.
Okay, if there are other questions, please feel free to ask. I had one kind of dumb question, I guess. On a few slides back, you had like PQ mapping to that one. Yeah, right there. How did that little picture with the 0R in it represent that the Q was squaring?
Yeah, because when you take your, if I go back really far, yeah, if you take your like Hamiltonian, which I've asked to be a quadratic function,
I see.
The linear part becomes like the affine part. the quadratic part becomes the linear part, and then the linear part or the constant part just like disappears. So
Okay.
in this picture, this is like the affine part, and that is like the linear part. And there's no, the constant part is just gone, basically.
Mhm.
So
And if you were to say like, this is a very different kind of question, the decade of physics where you kind of are right now, or something like where you, if you had had this at that time, you would be publishing right alongside of the people who are making this stuff up. Kind of where do you think you might live? I don't know if that question makes sense to you, but what time
I don't know.
are we
I
here?
just find like I can only imagine myself now because, or maybe in the 80s onwards, because like physics didn't used to be like so mathematical. So I would probably just be
Mhm, mhm.
confused.
Right.
If you mention like category theory, like there
Yeah,
was no
no,
such, mathematical physics had not got to that point. So I would probably just be like,
yeah.
I would fail my physics degree.
Okay. Well, it's very cool. I don't know if there are any other questions. Seems like there's not, at least while the recording's on. So I'll stop the recording and turn off the live stream. Um, Give me a second to do that. So the live stream is done.